All right, everyone. Welcome to class. Like I told you last week, I'm not there. In fact, I'm recording this video from a hotel room in Houston at the moment. So sorry I can't be there for today, but you're still stuck with me, or at least a one-sided me, since I can't really answer questions. But I'll be back on Wednesday, so I will see you then. But we're going to go through a few things, and then we're going to take that group quiz. And then we'll do some notes, and then you'll have some time to work on some practice problems. And after that, if you get done with everything, then you're good to go. You'll have some time to work on other classes if you want. So here is the lab that we had last time, right? We did the roller coaster lab where we had a marble that started up here, and then it went down, then it came back up, and then it went back down like that. That was about what the track looked like. And we were taking a look at various things along the way. So, these first few questions, let's just kind of go through them. How are speed and height related on the roller coaster? Well, we know we start off with some height, and at the places where we have the highest height, we also have the lowest speed, and the places where we have the lowest height, we have the highest speed. So it almost seems like as height goes up, velocity goes down, and vice versa, right? So they would have to be inversely related. I know a few of you were looking at this a different way in terms of what happens if the roller coaster was higher. Then yes, it would be going faster down there at the bottom. That is also a true relationship. It's not quite what the question is getting at, though. What is energy? So we have a definition from last class, so I'm going to let that one go for you. How are energy and motion related? Well, we know we can't have kinetic energy, right? Kinetic energy, it has to do with motion, right? So there's no kinetic energy if we don't have motion. Potential energy doesn't necessarily require motion, but potential energy could turn into motion, so that is one way that that's related. And then how is energy converted in a roller coaster? Well, we know we start with quite a bit of potential energy, and we know down here at the bottom we get some kinetic energy. We convert it back into potential and kinetic, so we have this thing called conservation of energy, or conversions of energy from one form to another. So that's what's going on in a roller coaster. Let's take a look at some data. So this is data I took before I left. Hopefully your graphs look fairly the same. Remember that for your total energy, remember that for your kinetic energy, which is the blue one, you have to use the 7/10 mv squared. If you are seeing some issues with your graphs, it could be maybe that you didn't use the 7/10. Remember, the 7/10 is different from what we had in the notes because we have rotation going on in that marble. That's the reason why it looks a little different. So what are some things that we notice? We notice that the potential energy seems to go with the height, right? So it starts high and then goes to a lower point and goes to a higher point and then goes to the lowest point where we have the lowest part of the ramp. So potential energy seems to follow the actual physical location of the marble on the ramp. Kinetic energy seems to be pretty much inversely related. So as potential energy goes down, kinetic energy goes up, and vice versa. But if we plot the sum of those two, the potential and kinetic together, then we basically see a nice kind of flat line here. And I know I did this as a smooth line curved graph instead of, and you're not really supposed to connect the dots. I was doing that for the benefit of these graphs down here. But we pretty much see a total energy that is relatively constant, maybe dipping slightly. So why would it dip slightly? Maybe because there's a little bit of air resistance slowing down the marble as it goes. I really don't want to say friction here, and we'll talk later, but friction is actually the reason why the whole thing rolls, and it doesn't do much to slow it down. So we can say air resistance. So there's some questions here. So like, what happens to the potential energy of the marble as the kinetic energy increases? Why do you think this is? So that could range from anything from, well, we know as the potential energy goes up, the kinetic energy goes down, or vice versa, because we're talking about as the kinetic energy increases. So that would be as it gets faster. We know the marble is rolling down, so the potential energy has to go down. Why do you think this is? Well, we can see from the graph that it seems like no matter where we are, we have to have the same amount of energy. So if we know the kinetic energy is going up, right, then that means we have to be getting that energy from someplace. We're not manufacturing it. We're not getting it out of nowhere. So we're having to take it from the potential energy. So any increase in kinetic energy is taken from the potential energy, which is also showing how the height goes down. What happens to the mechanical energy of the marble as you move further along the ramp? Well, mechanical energy being the sum of kinetic and potential, that's this guy, mechanical energy, we can call it ME, that's me, and we can see it's pretty much constant. So there's not really anything going on with it. If you want to, you can throw a statement in there about how it goes down slightly, and that's probably due to the little bit of air resistance going on that marble. So what about over here? Question 3. According to the law of conservation of energy, energy can't be created or destroyed. So if this is true, explain what the total energy graph should look like. Is mechanical energy conserved? Is the total energy conserved? Explain. So, mechanical energy. Remember, mechanical energy is that potential and kinetic. So if we were in happy physics world would mean no sort of resistance whatsoever. Resistance. I'm drawing with my finger. Hopefully you guys can read that. We would notice that it should be a flat graph. That is a very flat graph. Maybe that way. It kind of goes. So it'd be a flat graph. Shouldn't go up, shouldn't go down. Now what do we have? We have one that possibly deviates a little bit, and I'll do this in a slightly different color. It goes down just a little bit. So is mechanical energy conserved? Well, if you want to talk about happy physics world, we'll say yes, mechanical energy is conserved. But if we're talking about real world, we can say, not really. Mechanical energy is not conserved. But if the law of conservation of energy says energy cannot be created or destroyed, then how does that fit? We'll go back to that definition. It is just as energy, right? Energy can't be created or destroyed. And mechanical energy is kinetic plus potential. There's other types of energies. We talked about this. So what other type of energy could possibly be there as the marble was going down the ramp? Well, could you hear it, right? If there was sound coming from the marble as it rolled, maybe that's where some of that energy went. So maybe the dip is not necessarily due to all air resistance. Maybe it was because some of that energy got converted into non-mechanical, right? Non-mechanical forms. And so therefore it went away from the system, and we wouldn't have been able to catch it on the graph, right? Because the graph was just looking at those two, kinetic and potential. All right, so what about number 4? If you repeat the same experiment using a lighter plastic marble instead of the steel one, you would measure that all the velocities were the same. So if you went back and used the photo gates at every single same point on the roller coaster, you would see that the velocities were exactly the same. And we have seen many, many times where mass is unrelated to how things move, especially when they're falling due to gravity or rolling down a ramp or whatever. So the same, or sliding down a ramp, I should say. So the same thing is happening in this roller coaster. Mass does not matter when it comes to the velocity, when it comes to the motion. So is the max potential and kinetic energies of the heavier steel marble bigger, smaller, or the same as the plastic marble? Well, let's think about how do you calculate potential energy, right? mgh. How do you calculate kinetic energy? 1/2 mv squared. We're not doing anything to the heights, right? So the height's not changing. We're not doing anything to the velocities. That's not changing. But both of these individual formulas still depend on mass. So if we're talking about potential energy and kinetic energy at any given location, a lower mass, right? A lower mass, because we're using a plastic one, would mean that we have lower potentials and lower kinetic energies. So therefore, for that plastic one, it would have to be smaller than the heavier one, right? Even though the heights didn't change, even though the velocities didn't change, because the mass is different, the energies are the same, which is weird. So what we would see is these graphs would be exactly the same shape, but our scaling would be different, right? It would be still same constant mechanical energy, still same shape of potential and kinetic energies, but they just wouldn't be as much. Okay, so what about with starting? Is the starting total energy of the steel marble smaller, bigger, or the same as the final total energy of the steel marble? I lost my train of thought. So is the starting total energy of the steel marble bigger, smaller, or the same as the final total energy of the steel marble? I think this is supposed to be plastic, because we have already talked about the steel one. So let's talk about the plastic, right? We're redoing this with plastic. So if you repeat the same experiment with plastic, so is the starting total energy of the plastic marble bigger, smaller, or the same as the final total energy of the plastic marble? Well, we would see that even though potential and kinetic energies both go down, if you compare the beginning of the track to the end of the track for a given set of data, hopefully you would see that it's still the same. Now here it's pretty much all potential, here it's pretty much all kinetic, but we would still have the same total energy. No matter if that total energy was smaller than what it was for the steel marble because it was heavier. Total energy does not change. Now, in the real world with a plastic marble, you may encounter a little bit more air resistance than what the steel marble did, and so maybe you'd actually see a dip that's a little bit bigger than what you saw in this one, but that's because of real-world effects of air resistance, which we don't get into. We're going to assume everything is in happy physics world, where friction does not matter. Okay, what about this last one? If there are a spring catcher at the end of the roller coaster that displayed the maximum compression distance of the spring, would the max compression of the steel marble be bigger, smaller, or the same compared to the plastic one? So we're basically saying as it comes down off that last ramp and hits a flat part, and there is a little thing that, little platform attached to a spring, and when that marble comes down, it hits and obviously compresses the spring to maybe right here. There's a little readout that tells you, how much it got compressed. So we're basically saying, so if the velocities aren't changing, right, the steel marble, plastic marble, you still are going to end with the same velocity, then what is that going to do to the compression of the spring? Well, let's think about it, right? We have kinetic energy here, and then it's going to compress that spring, which means it's going to turn into potential energy. And this is not gravitational potential, it's going to be elastic potential or spring potential, right? So that spring potential has to do with that a compression of the spring, right? 1/2 kx squared. So x is the compression. So if we completely stop the spring, that means all that kinetic energy would have had to turn into potential energy. So which one has more kinetic energy when it hits? Even though it's the same velocity, right? Same velocity does not necessarily mean same kinetic energy, because if you have a larger mass, then you're going to have a larger kinetic energy. And if you have a larger kinetic energy turning into potential energy, that means you're going to have a larger x. So which one's going to compress more? Well, the steel one's going to compress more. So the way the question is phrased is the maximum compression of the distance of the spring with the max compression of the steel marble be bigger, smaller, or the same as the plastic one. So it would have to be bigger. The steel marble is bigger. Okay, so hopefully all that stuff was clear as mud. You can work with the people at your table, and you are going to take this. So this would have been posted to Google Classroom this morning. So you can take the Roller Coaster Lab quiz. You can use your lab that we just went through. You can use the people at your table to help you understand the questions. It's not very many questions, something like 5 questions. Yeah, so this is what you're going to do. So if you could please pause the video, and then everyone can go grab a Chromebook. You can also do this with your phone if you would like, but you are allowed to work with the people at your table, the people that you did this lab with. There shouldn't be any yelling across the room or talking across the room. You should be working with the people just around you. Get this done, get it done quickly, because we have more stuff to do. So pause this video. All right, welcome back. So hopefully you will have finished this quiz already, and we are ready to move on. So you should have picked this page up from the tray by the door. This is the notes that we're going to go through today. It's not too terribly difficult. Some of this stuff you probably have already gone through a little bit before, but we're going to turn this idea of conservation of energy into a little bit more math. The problem with this unit, what makes this unit difficult, is that we really don't have a set equation. We kind of do. It's this guy right here. We'll talk about it in a second. But really, each individual situation is going to determine its own equation. So we have to figure out ways to do this, ways to make this a little bit easier for us. So hopefully what we do today is going to help streamline the process and help you get to that end state a little bit more quickly. So what are we talking about? We're talking about the law of conservation of energy. If the total energy of a system remains constant, there must be no external forces acting on the system. So that's going to be important, because that's going to designate what we need to have in the system. So no external forces. Energy must remain constant if there is no external forces in the system if we know energy is constant. Energy can be created or destroyed. It can be changed forms, but the total amount has to remain constant. Again, if that is true, then we know there are no external forces. But we're going to focus just on mechanical energy of a system. So we're not going to talk any about whether sound is present and releasing some energy, or chemical energy in the food that Tarzan ate. Because you see, we're going to talk about Tarzan here in a second. So we're only going to be talking about happy physics world, total mechanical energy of kinetic and potential. So, technically speaking, though, you can have both potential energies, so you can have something jumping in there and then compressing a spring. So we're going to talk about just kinetic and total potential, meaning gravitational and elastic or spring together. Let's just jump right in. So we have Tarzan standing on a 20-meter high cliff, swings on a vine to the jungle floor below. How fast is Tarzan swinging when he reaches the jungle floor? So the thing we always do is drawing a picture. So here we go. Here's a picture. There's Tarzan. My Tarzan looks really great. It would be much better if I had a stylus. And he swings down here to the jungle floor from his vine, right? So what do we know? The jungle floor is 20 meters tall, and we have no idea what his mass is, but we'll see here in a little bit that we don't even care. Okay, so we have a kind of a good idea of what's going on. Now, we are going to do something called drawing an LOL diagram, because, you know, we lol all the time. Yeah, I just said that. I'm sorry. I should never say that again. LOL. Well, the reason why we call it LOL is, you're probably going to remember it, LOL, but it's because what we're going to do literally looks like the letters LOL. So in that space, and I'm going to do this a little bit bigger on the next screen, you're going to draw in LOL. So take a couple seconds and draw in LOL just like I have here. Okay, so these L's are not actually L's. They're going to be bar graphs, and we are going to try to maintain information about energy before he swings, Tarzan swings, and then after he swings. And we can only take a look at basically a single action, before and after, or at one point and then another point in a given process, and that's what we're going to be doing here with Tarzan swinging. So we need to include things in our system, and that's actually what this one is for. It's for designating our system. So remember, we only know energy, or energy is conserved. We know there has to be no external forces. So we have to construct a system where there's no external forces. So if that's the case, Tarzan is one thing that's going to be in our system. He's the one that's containing kinetic energy, and so we need to have him there. But in order for us to talk about potential energy, remember that systems, only systems containing multiple objects can contain potential energy. So we also have to put in the Earth. Now that helps us, because that means that the force of gravity is no longer an external force, it's an internal force. The Earth and Tarzan both being in the system mean that they pull on each other, and that force no longer becomes an issue for energy conservation. So before, let's go back to our diagram, right? Before, we're up here, Tarzan's up here, Tarzan's not doing anything, he hasn't dropped yet, he's way up in the air, which means that out of our types of potential energy that we have this certain amount of mechanical energy, and all of that mechanical energy is gravitational. We don't have any kinetic, we don't have any potential that is spring or elastic. So our bar chart is showing us that our mechanical energy here, you can color it in if you want, is all gravitational. But what about after? So after, he swings all the way down here, where we are at the lowest point. So we're going to say that height is equal to 0 down there. That's our reference point, because we did pretty much imply that by saying we were 20 meters above the floor, so that's our height. So we'll say that now our gravitational potential energy is 0. We still don't have any elastic potential, and we know we don't have any external forces to the system, so that means we have to have the same amount of mechanical energy. But where's that energy? That energy has to be all in kinetic, and so now our bar chart is there in kinetic. So same amount of mechanical energy as we did before, but now it is kinetic. So our LOL diagram is really showing us that, hey, what we did is we started with gravitational potential, and again, seeing that this bar and this bar are the same, that gravitational energy turned into kinetic energy. So how's this helpful? Well, when we come over here, we're going to write the conservation of energy equation. So the conservation of energy equation should always start like this. If we know energy is conserved, we'll say that the initial energy has to equal the final energy. right? The initial energy has to equal the final energy. That's just a statement of conservation of energy. College Board loves seeing statements like that because then they know you know what you're talking about. So let's go back over to the LOL diagram. What was the initial energy? Well, the initial energy was gravitational. The final energy was kinetic. So when we come back over here, the next step would be saying, okay, that means the initial gravitational potential has to equal the final kinetic. And then we can substitute the formulas in for each one of these. So this would be mg multiplied by the initial height, and this would be 1/2 mv squared, where that's the final velocity. And hey, look, that's what we want, right? The final velocity, how fast is Tarzan moving when he gets to the floor? So now we just solve this, right? We solve the equation for the requested value. Well, if I rewrite it, mgh is equal to 1/2 mv squared, we notice, hey, look, masses cancel out. We don't need to know what the mass of Tarzan is. This is actually the reason why the mass doesn't matter in the roller coaster lab, because as you're transferring from potential to kinetic, both of them depend on mass, and both of them depend on mass in the same way. So that means that any changes in one would be the exact change in the other. So that means that v squared would be equal to 2gh. Where did I get the 2 from? Well, that's coming from the fraction here, where I just multiplied the 2 to the other side. So there's my algebra, right? So I solve for the equation, and I would actually take this and do a square root, so the square root of 2gh, and then I would plug in values, so that would be the square root of 2 multiplied by 9.8 multiplied by the height of 20, and that gives you some value. Gives you value around 19.8 meters per second. And it's as simple as that. So again, if we go through this in a highly systematic way, then it becomes a little bit easier to handle, right? So what do we do first? We draw a picture. From that picture, we construct an LOL diagram, really taking a look at what's in our system, what's not in our system, what do we need to have in our system for conservation of energy, and then using that diagram to build an equation, and then the rest of it's just algebra. So let's try it again. So Tarzan, in an attempt to escape a gazelle, has gone mad, is running on the jungle floor at 10 meters per second, and he swings on a vine toward a 10-meter tall cliff. Will he make it safely to the top? So what do? We draw a picture, right? So here is our picture. We know that this thing is 10 meters to the top. He's got this vine here, and he's running. So that running is hopefully going to swing him up to the 10-meter tall cliff. Now this is a little bit different. That 10-meter tall cliff is now just a reference point. We don't know if he actually goes 10 meters up. So if we do an LOL diagram, we again need to have Tarzan and the Earth in our system. And this would be, again, a before picture and an after picture. We can kind of trim this down a little bit and say that we don't really need any elastic potential. So why not have that? We having the Earth in the system means that we, again, don't have any external forces to the system. So we would then say, okay, if we have a conservation of energy statement, then at the very beginning it's going to be all kinetic because he's on the floor and he's moving really fast, and the speed is 10 meters per second, and then that turns into gravitational potential energy. So we still have conservation of energy. That kinetic at the beginning has to be the gravitational at the end. So then we write that, right? Conservation of energy says that our initial energy has to equal our final energy. And our initial energy, according to the LOL diagram, is an initial kinetic. The gravitational potential energy is what we have at the final, leaving us with an equation that looks very similar to the one that we just had. It's on the opposite sides, where with the initial kinetic energy, 1/2 mv squared is equal to mgh, and the masses cancel out. Again, we're looking for height this time. How far does he actually go up? So our hf would be equal to VO squared over 2g, using the algebra, right? I just divided the g to the other side, and I pushed the 2, I just wrote it differently, right? V squared on top and 2 on the bottom. So that would be 10 squared over 2 times 9.8, and that is roughly what? So 10 squared is 100, divided by 2 times roughly 10 of 20, so 100 divided by 20 is going to be roughly 5 meters. 5 meters. So does he make it to the top of the cliff? Nope. That's our answer, right? Because the question is, will he make it? So we have to answer that question. So no, he doesn't make it. So why don't you try this one? So why don't we pause this video and I'll give you a few minutes to try this one on your own. It's a little bit different. It uses spring potential rather than gravitational potential. So try it on your own. So there's my work. Should just popped up on the screen. So you can check yourself. Did you get 10.4 meters per second? If you need to, you can pause the video and see if you can make sense of my work, right? Potential energy spring that turns to kinetic energy final. Okay, so what we're going to do next is you're going to get some papers. You're going to get 3 papers, actually. I'm showing you 2 right here, so I'll go back to that. You're going to get 3. One of them is going to be blank. All right, you're going to get 3. So why don't we pause the video and hand out these 3 papers. Okay, so you're going to be constructing a foldable, and I've got an example there on the table, or on the front table, but I'm going to try to walk you through this in pictures, and it always doesn't necessarily work out all that well in person, so hopefully you can follow my pictures with this. So you're going to take these 2 papers, and you are going to lay them on your tables like you see them right here. So make sure that you have the problems on the bottom, the images on this one right here. There is actually writing on the back side of this one at the very top, so make sure that that is on the underside. But you are going to get a third one. You're going to get one that's completely blank, and you are going to layer them. Okay, you're going to layer them on top of each other. So the blank one is going to be on the bottom. The one with the images is going to be in the middle, and then you're going to be the one with the problems on top. And they need to be layered so that there's about, I don't know, a half an inch or so of space in between. So they're going to sit layered on each other. Okay, but you got 3 of them. So then what you're going to do is you're going to fold them so that you create a foldable that has 6 tabs. So basically you're going to try to take this entire thing and fold it along a line that's about like that. And what happens is if you do it right, you end up with something like this. So you fold it just above where the problems are, and those numbers that you saw that were face down earlier are going to be the things that you see on the very, very bottom. So that's going to be the foldable that you're trying to create here. Okay, each one of these tabs is going to be labeled something very specific. So what you'll do is on the first one, you'll label it problem. The second one, you'll label it diagram or picture. The third one is LOL. The fourth one is conservation of energy. The fifth one is algebra. The sixth one is solve. So pause the video if you need to, or go back and watch a part again. So want to get to a point where everyone has all the foldable done and labeled. Okay, so this is basically 4 sample problems, or 4 problems for you to work through this process. I have, on my example, 1 done. In fact, I've got this one done for you. The rest of them you can do on your own, or try to do on your own. And if you have any questions with this, you can ask when I come back on Wednesday. That's the one I've done for you, so I'm not going to worry about going through it. Okay, so once you're done, you can pick up this, but you need to make sure that you get it before you leave. And this is basically a sample problem. Gazelle leaps up straight up in the air at a speed of 6 meters per second. And it's a way for us to go back and forth and take a look. Okay, we could solve this using kinematics. How do we do that? A long time ago, at the very beginning of the year. And then now we can do it with kinetic energy, or with kinetic energy turning into potential energy. So the idea is for you to solve it both ways and see the similarities, see the differences. There's some graphs down here, so we're reviewing a little bit of kinematic graphs, but also a little bit on potential energy, kinetic energy, and that sort of thing. So keep in mind what it looks like with these graphs. One's with time, one's with position, so keep an eye on that. So that is what you're working on for the rest of the class, the sample problems on the foldable and this guy. So get to work, and if you finish early, great. If you have questions, I will be back, or you can always go and ask Miss Rittenhouse next door. You guys have a good one, and I'll see you when I get back.